This video, we're going to go over kinematics of a particle, Chapter 12, Section 1 and Section 2 of Hibbeler's Dynamics. So we're going to discuss solid mechanics. And solid mechanics is the physical science that deals with the state of rest or motion of bodies. So last semester, or previously, you discussed statics, which dealt with the mechanics of bodies at rest. And in this video, again, we're going to talk about dynamics. And in particular, we'll talk about kinematics, which is the analysis of motion without reference to any forces. And we will also later discuss about kinematics, or kinetics, and let's spell this correctly, kinetics, which is the analysis of forces on bodies causing motion. Section 12.2, rectilinear kinematics and continuous motion. The kinematics of a particle can be characterized by three quantities: its position, its velocity, and its acceleration. This is how we're going to use kinematics to characterize particles. Let's begin with position. The straight line path of a particle can be defined by a single coordinate axis, as such, with an origin. Well, I guess we're going to go with red. With an origin here and the position of the particle represented here. This is the magnitude of the distance of the particle from the origin. We'll just label that S. At some point, the particle may move to a new location and have a change in its position by the amount of, say, delta S. So the overall position of the particle here, we might say is S prime. So S prime equals S plus delta S. And if we just want to rearrange this, we could say that delta S, if we want to focus on delta S equals, let's draw that a little neater, delta S equals S prime minus S. Now in this situation we're describing here, let's agree on a convention that if we head in this direction, we're just going to call that arbitrarily positive, and if we head in this direction, we're going to call that negative. So that's our sign convention, and it is arbitrary, but we need to describe it. Let's move on to velocity. So if we have velocity, if the particle moves, and velocity has a, in vector format, velocity has a magnitude and a direction. Speed is just the magnitude of velocity, but let's consider that our particle moves some delta s in some time increment of delta t. So this is a change in position as described above. In some time interval delta t. Then we can describe an average velocity as v average. If I put a little tail on a v, I'm kind of indicating that's a small v, equals delta s over delta t, or the change in position divided by the change in time. We can represent this velocity by, say, plotting s versus t, and say we have a path here. Then this is the position of our particle at S1 at time 1, and the position of our particle, say, at time 2, some other position at time 2 is here. Then we can calculate our delta s versus our delta t here by just taking, and we can look at this change in our position with respect to some delta t as simply s2 minus s1 divided by t2 minus t1. If I connect these 2 points with a secant line here, so we recognize this then as the average rate of change of s, or the average velocity. And again, this is just the average rate of change of the particle. So now, if I were to make this delta t here smaller and smaller, then you would see that the slope of this would change, and eventually this, if we made delta t small enough, this would change into the slope of the tangent to this curve at the point S1. It's hard to get this to land back on the point that I selected there and make this look like a, I'm just going to delete this and hand draw this as best I can, and that wasn't very good, so let's try again. I don't want to go under the line really, but so here we go. So so if delta t gets smaller and smaller and smaller, we end up with a tangent to S1, and we can represent this with calculus with the idea that if we take the limit, oops, I don't want a big there. If we take the limit as delta t approaches 0 of this delta s over delta t. Well, this equals dt, ds dt, which we define as the velocity. And this is the slope of the tangent to the curve, in specifically the position as a function of time curve. Okay, let's move on to acceleration. So, using a similar idea, acceleration So let's talk acceleration. So the average acceleration then can be defined in a similar fashion as the change in velocity with respect to the change in time. So the velocity is defined by the change in position with respect to time. So the acceleration then is a continuation of that. We can, of course, produce our instantaneous acceleration by taking the limit of that as delta t gets smaller and result in a relationship where the acceleration equals the derivative of the velocity with respect to time. And this, in fact, is now the instantaneous acceleration at a particular point. And this was the average acceleration, or the slope of a secant line between two velocities on the velocity as a function of time curve. So I can look at this now, this equation here, and I can say sub in the derivative we had for velocity and come up with A equals v dt, which equals the derivative with respect to time of velocity, which was ds dt, and this equals the second derivative of our position with respect to time. Let me turn off the ink to shape and redo that. Just changing it into a geometry. And we end up with this result. Another way of looking at acceleration. So observe, if we play around with our equation a little bit, we start here, say, with ds dt equals velocity. We can use some algebra, and we can move these terms around. dt equals ds over v, and then we know that we define that dv dt equals acceleration. And let's monkey with that. Solve it in terms of dt again. We get dt equals dv over a. So combining these two, setting them equal to each other, we can end up with ds over v equals dv over a. And I want to get another relationship for acceleration, since we're talking about acceleration here. I can then use my algebra again and end up with a equals v dv ds, which eliminates our differential respect to t from this relationship. And that's also another useful relationship.